picking up where we were. So the guys on Sunday seem to have, they're saying that what they're going to cover is page 601 to 606 of the book, which is starting from progressive growing of GANs.
Yeah.
Through to style GANs. So yeah, so let's us do that as well. And yeah, we'll catch up probably about 50 minutes past. Is that okay?
Yep.
Cool.
Yeah, that works. Yeah. I'll talk to you then.
Okay, speak to you then.
Cheers.
Right. Bye.
Bye.
Oh, hey, Otto.
Hey.
Oh, hey, Dinesh.
Yeah.
Okay, let me share my screen. Yeah, I really struggled with this stuff. I really don't know enough about GANs, and mind blown.
Yeah, a lot of stuff here, like a new stuff.
Yeah. Did you guys have a chance to go to the Sunday one? I missed it again, which is like a real shame. I'm going to have to listen to the recording.
Yeah, I was attending Sunday session.
Yeah.
Cool.
I was there as well. I'm like, but I was half there. I didn't watch it too much. But yeah, it was really interesting. Joseph did a great job. A lot of discussion. So I guess worth watching the recordings.
Yeah, I might do that tonight. Okay, so getting started on the progressive growing of GANs. So yeah, so these guys, they suggested another approach to generating fairly large images, and they said, what we could do to try to do was to gradually increase the size of the image. So the idea was so maybe we were start by a 4x4, and then you were trying to do an 8x8, and then 16x16, and then 512 by 512, and then 1024 by 1024. And this approach resembles greedy layer-wise training of stacked autoencoders. So we saw it last week, actually, where I think this was originally proposed by Geoffrey Hinton as a way of training neural networks, which was to kind of train them kind of a couple of layers at a time. And then kind of stack the pre-trained on top of additional ones. And I guess this was in the old days when maybe the graphics cards couldn't handle like a huge amount of parameters, and this was one way to get around it. But they're using this approach in a slightly different way now, purposefully, to try and see if they can get it to generate bigger and bigger images. Is that kind of okay, or does that make sense?
Yeah. So I'm like, what do you mean by training separately and putting it together in a sense?
Yes, so I don't know if you remember, but the autoencoders, they've got these layers in the encoder, and then these layers in the decoder.
Yeah.
So one way to train it is to do it all completely end-to-end in one go, just like a deep network.
Mm-hmm.
A slightly different way to do it is to take the two innermost layers in this network, so the ones that are right in the middle, and then train first the two outermost layers to on the data, and there you've only got two layers now: one input layer, one output layer.
Yeah.
And then what you do is you apply that to the data to get the input and output pairs now, and you add on another layer which is training on this data now. So gradually you kind of add in the inner layers, kind of two at a time, until you've got the full end-to-end.
So what difference it makes? So you're saying in the first go we will have one layer, inner layer, and then the second go we're gonna have a two inner layer, and third go we're gonna have three layers. Is that like sequentially we are adding layers?
Yeah, so it's a little bit different. So it's two layers at a time. So the very first in network is the very outer encoder layer and the very outer decoder layer, and then that's kind of one training loop that goes through. And then there's a second one which adds in another, so the next set of layers, but assuming the first ones are now being kept the way they are. So basically, you don't even have those in the network anymore. You just use them to apply to the data.
Okay. So the weights for those layers kept freezing while the additional layer get trained. And then in the next loop, you'll have the four layers, two of the first two and last two, they are frozen, and then two newly introduced layer will get trained. So sequentially training two layers at a time.
That's right, yes. And what Jeff Hinton had kind of proved was that this was possible, and you would get kind of the result you would get if you did it end to end, that there was some kind of relationship between the two. I haven't read Jeff Hinton's paper, but we don't do this as much now because our graphics cards can handle kind of like fairly large networks. But I'm guessing this was in the days when graphics card couldn't, and this was one way to train deep networks, was to do them kind of these kind of 2 layers at a time.
Did they freeze them though in this particular
yeah, so it's sort of pretending to freeze them, because what they did was in the old days they would train the 2 layers, and then what they would apply the input to the first layer and take the output of that, and then take the output of the second layer and get the output of that. And the idea is that you've kind of you've trained the network, the two layers, and then you apply the data to it to get a new data set, pretending that you've actually applied those 2. Yeah. And then you use that data to train the next 2 layers. So instead of like getting the network to become deeper and deeper, every network has always got 2 layers in it, but it's the data that changes, which is what has the effect of having the weights being fixed. I don't know if you quite get what I'm saying. Because the network never actually grows. You never have a final network which has got 16 layers in it. Every network's only got 2 when you're training, yeah? But it's the data that changes. So the very first data is what you had as the original input. And then the final output is what you had. But then the next stage of it is the input is now modified by applying it to the input layer. I'm guessing, so what did they do with the output? Because, yeah, I mean, the idea was that it was the data set that was, so yeah, I guess the output would always be the output. It's the input that keeps changing. But the idea was that it's the data that's transformed. So you've trained the network and you apply it to the data to get a new data set, kind of pretending that the network is working at that level. And then you train the next 2 layers on that kind of transformed data.
Okay. Yeah, but that block scheme on the next page, how do you interpret this?
Yeah, so this is, so what they're saying is, so this is kind of like, say, this is phase 1, which is this the smaller network. And then, so this is greedy training, which is where we've gotten some, there's some input and output is in there. We're training this really tiny little thing, yeah? Yeah. And then what we're going to do is we're going to take kind of what we've got already and kind of pop some stuff into it. In this case, we're actually still keeping the whole network end to end, because we're not doing what Jeff Hinton was doing, which is to kind of just only go with the new stuff. And actually, the data, the output of this bit, which in theory, he would have kept static, he would just take the output of this bit and feed it into there. And then train it on the final output. But yeah, but in this case, it's slightly more complicated, but what they are saying is that we train this bit first, and then we introduce this additional thing to upsample it, and we train that whole thing, and then we do another sort of thing which sort of applies to that, which kind of increases the size of it again, and then we add another one eventually. So it is a bit like the greedy in that you start up with a small network and gradually it's getting bigger and bigger at each stage. But we're not fixing this now because we're still doing it end to end. But they have got some slight fixing to do through this alpha parameter.
So in this case, they grow network progressively and keep training it like all the network. But this alpha parameter, it helps you. It's like, as I understood from the book. Okay, we'll get to that, right?
Yeah, but I mean, the idea is that eventually, once you've trained this, because alpha is 1, you can chop out this bit and then just keep that bit. Yeah. So the next one along, won't have this bit, because this, the output of this is being completely removed. And then so the final result of this is actually, after you've fully trained it, is you can actually get rid of this bit and just keep that bit, because this is the bit now that's adding in the addition, the upsampling is done. Yeah, I mean, you don't need this once you fully finish because alpha will be 1. And so the output
it's
of
like
this is
warm start in it, right? Like we have this trained out conv, which is the first one, which is transferred from the previous stage, and we add like this.
Yeah, this path here.
Yeah, this path, and we like have some combination of those two. And in the beginning, we will have it more using this path from the previous stage, but towards the end, we will like remove it and switch to that right path, right?
Yeah, yeah. And so when you finally resolve, you can actually, in theory, ignore this one altogether because all the data will be going through this direction. But you're quite right. While you're training it, you're also almost sort of transferring what's here to kind of there. And obviously getting some extra stuff because there's 2 layers now instead of just 1.
So why we are doing it like the way we are doing it? So what's the purpose on the left side then?
Well, what it is, I mean, I'm still not clear how they go from a 4x4x3 to an 8x8x3 and sort of copy the weights across. No, I didn't get an explanation of that bit. But if we ignore that bit, so
yeah,
I mean, okay, so let's say the
original
original network was this one, yeah?
Yeah.
Yeah. And the idea is that this one was originally trained by a 4x4, but we've kind of just upsampled it to an 8x8, yeah?
Yeah.
So the results probably not fantastic because, you know, there's not like a huge amount, you know, it's still the same network, but this has just been upped, yeah?
Mm-hmm.
So what this is doing is, so this is doing adding, so this is first of all, going to from 512 features to 256 features. And then, yeah, so this additional structure, I'm not quite sure why they've reduced the number of features from 512 to 256 there, but okay, that's another question. But long story short, it's just a question of, to get like output which is bigger, you're going to need kind of more stuff going on. You can't just rely on this just one layer to do everything for you, to go from a 4x4 to an 8x8. So, you know, my understanding is that you need kind of this additional structure to be able to get something decent out of an 8x8, which was originally trained with a 4x4. Yeah.
Yeah. So my only confusion is I understand that you upsample, you go from 8x8 by 512 and 8x8 by 256 and an 8x8 by 3 and then alpha and then 8x8 by 3 finally, you know. So
yeah.
why they have the first I'm talking about the right figure, first pass. Why?
So this
why
one.
show that? Yeah. Why to show this first pass at all? Why don't we just say you upsample, you go 8x8 to 512, and then 8x8 to 256, and then 8x8 by 3, and then that's pretty much it. So why they have this kind of like get the right portion on?
I think the answer is highlighted in the text here. This to avoid breaking the trained weights of the first convolutional layer, right?
Yeah, so part of, I think what you're asking, Dinesh, is why can't we just fully train this end to end to up to 1024 by 1024? Why do we have to go through this convoluted thing where we're doing by 4x4 and then 8x8 and then 16x16, if finally growing it to be the full size that we want it to be? Is that sort of your question?
My question is they have done this dotted line.
Yeah.
My question is why they have done this dotted line. Why don't you just superimpose that dotted line to the left and just say that's the path?
I mean, intuitively, what they're saying is that if we ignore this section here, this was what the original one was. Yeah. It's a little bit bigger now because it's 8x8 rather than 4x4 because of this upsample section here. But in essence, this thing here is what the network was originally doing when we trained it, you know, when it was like that. Yeah, it's gone to a slightly bigger size, but essentially all the weights have kind of been transferred over into here in some clever way. Yeah.
Mm-hmm.
And then what they're saying is what we would quite like to do is to get all that training that we'd already done transferred over to this side, in a slightly deeper network with a bit more in it. So we want to take what we learned here, transfer it over into there, and then hopefully get better result, because we upsampled it. So, the output of that straight away won't be great, but if we kind of have what it was and transfer it over to here and have some extra structure, that this is what's going to give us what we want. I think that's what I understand. So I don't know, Otto, what you think?
Yeah, I think he has like a good explanation here in the text. So what he says is that so this is done to avoid breaking the weights of the first convolutional layer. And how do I interpret this? So the first convolutional layer, which is between dense and upsample, it's trained, and we want to utilize it as much as we can, because otherwise it would make no sense to do this progressive upscaling. And if we just replace the previous outconv layer by 2 new layers, which are initialized randomly, we will just, with the very first backpropagation step, we will just ruin all the training we done for the conv1 layer, because we keep training it, so it's not freezed. And their first weight update will be highly determined. The first weight update for the first convolutional layer will be highly determined by the random weights of the newly initialized weights. And by doing this fade in, fade out technique, we start with pretty reasonable this outconv from the previous stage. And yeah, so the answer to the question you had, how do they go from 4x4 by 3 to 8x8 by 3? I think there is upsampling is all we need for that, because convolutions, they do not depend on the input shape. So if you feed in 8x8 grid to the convolution, it will output 8x8 grid. And if you feed in 16x16 grid, it would output 16x16. It's the same filter, the same set of filters. It's just applied locally. So that's why we can do that, right?
Okay. Yeah, so, well, I guess for first answering what Dinesh was saying, Dinesh, are you okay with why they've done it?
Yes. Thanks to both of you. I think one of the point which I was missing, and Arshad, you explained to me in previous section, the point I was missing was progressively growing gap. So I think now I got the idea that first we train and then we progress to the next, introduce new layers. That's the point I was missing.
Yeah. So Otto, yeah, I mean, so my question about it really was, okay, so we've got some weights here for this convolutional layer here, yeah, this output layer. Somehow those weights are being transferred. I mean, I can understand the upsampling because that's the output of this guy being upsampled to 8x8. But the weights for this guy, they must be coming from here, because we want to keep the original weights so that, the backprop will not completely destroy this guy, as you were saying, because initially we're going to be taking the output of this one and it'll be pretty much 0 here because alpha is 0. So somehow the weights that were here have got to be transferred over to there, but the shape of the filters is different. This is an 8x8.
No, that's not a shape of the filters, that's the shape of the output. So these are exactly the same set of weights, but because we have a larger output here, input here, we have larger output. They don't specify the shape of the filters here. So 8x8 is a shape of the, we can say, of the image.
Right. Okay. So
we can keep just
it's the same way. Yeah, sorry, I fully understand now. I'd forgotten what convolutional networks are. Okay, yes, I get it. Because this is not the kernel. This is the output shape. Yeah, okay.
And another note about this 256, why they go from 512 to 256, I think it's similar to like regular convolutional networks when you want to keep the computation constant. So if you have a bigger input, like 8x8 input, you want to have less filters to keep the number of multiplications the same, right?
Yes, I got it. Yeah. Cool. Yeah, I understand that. I don't know, Dinesh, did you have any other questions?
Yeah, so 8x8 by 512, when it reduced to 8x8 by 256, that means the filter, we applied the 1x1 filter, or did we, so the filter got changed there to collapse the features from 512 to 256?
Yeah, so we used, I guess, a stride of 2 to bring that down. And the output was 8x8 by 256. Yeah, so I don't know what the kernel size was. But I think, well, I mean, we'd have to work out exactly what the numbers are, but what kind of Arthur is saying, I mean, the upsampling was a relatively simple operation, but convolutions require a lot of computation.
Yeah.
And by reducing it, by halving the number of features, but increasing the size of the network by doubling it, you've kind of kept the number of calculations to be the same as what it would have been originally.
Oh, okay. Okay. Yeah.
Yeah, so that kind of makes sense. That's a normal technique that they apply in a lot of convolutional neural networks. When you increase the size of the outputs, you reduce the number of features. Yeah.
Okay.
Okay, so and there's a couple of these like really weird kind of perturbations, might say, on the weights, and they do. Which, as I say, I don't have an intuitive understanding for. They do explain it here, so we might as well just read it. So there's a couple of additional things they do. Added near the end of the discriminator, for each position in the inputs, it computes the standard deviation across all channels in all instances in the batch. Okay, so we got a standard deviation. These standard deviations are then averaged across all points to get a single value. Okay. Finally, an extra feature map is added to each instance in the batch and filled with the computed value. Okay, so the standard deviation is computed in some slightly convoluted way and added as a new feature map. And then, so how does this help? Well, if the generator produces images with little variety, then there will be a small standard deviation across feature maps in the discriminator. Thanks to this layer, the discriminator will have easy access to this statistic, making it less likely to be fooled by a generator that produces too little diversity. This will encourage the generator to produce more diverse outputs, reducing the risk of mode collapse. Yeah, so I didn't really understand how this standard. Okay, so I can understand that it's computing a standard deviation. It's computing a feature map in the standard deviation. And if the standard deviation is very small, then it means that the generator is not generating any wide variety. So how is that like helping it? So
yeah, I think I can make up an example why I think this is useful. So imagine a generator producing, like, say we are generating that fashionist stuff, and let's imagine like a generator can produce perfectly realistic T-shirt, and that's all what it produces. So for discriminator to work properly in this case, it should stop grading that T-shirt as if we want discriminator to incentivize generator to produce something else than this T-shirt, its discriminator should start grading perfectly realistic T-shirt as negative, right?
Yeah.
And but if we add this extra term here, a batch of perfectly realistic t-shirts would have no like close to zero standard deviation. And it would be like a strong sign for discriminator to like strong indicator that this is like fake stuff, generated stuff. And I think it just makes much easier for discriminator to realize that this is like high quality stuff, but it's very similar, so it's generated.
Ah, right. Yeah, I think I got that. I don't know, Dinesh, did you have any questions on that aspect?
I mean, like mathematically, I still don't understand, but I understand what he's trying to say here. The mode collapse is, I think, the problem he mentioned a couple of sections back, that sometime the generator and discriminator go off the mode, in a sense. Sometime it generator keep producing one kind of image and discriminator keep on identifying it, so they get very good at it. However, then the generator is so good at it, it's keep on producing the same thing, but he's good at just doing one thing. He gets very diminished on the other images. So to keep, that's called mode collapse. So to keep the discriminator, the generator to keep on a track of producing a diverse output, to keep a discriminator to, I think, recognize different images. I think that's last layer get added in here. That's my understanding. Am I right in my understanding, or am I totally off?
Yeah, that seemed reasonable to me. Yep. Okay, and then the next section is that this slight difference in how the weights in these networks are configured, rather than using the where they're normally done. So it says all weights using a simple Gaussian distribution with mean 0 and standard deviation 1. So the normal method is, I think it's called HE, which is mean 0 but a standard deviation 1 over the square root of 2 n inputs, I think. This guy. So these weights, I guess, have a bigger standard deviation than you would with here, with this particular approach. And it says that but then they're going to have to do something to stop it from causing problems. But anyway, it says the paper demonstrated that this technique significantly improved the GAN's performance when using RMS prop, ADAM, or other adaptive gradient optimizers. Indeed, these optimizers normalize the gradient updates by their estimated standard deviation, so parameters that have a larger dynamic range will take longer to train, while parameters with a small dynamic range may be updated too quickly, leading to instabilities. By rescaling the weights as part of the model itself, rather than just rescaling them upon initialization, this approach ensures that the dynamic range is the same for all parameters throughout training, so they all learn at the same speed. Yeah, that's an interesting kind of. I must confess I'm not an expert in these optimizers, but yeah, that's an interesting approach to setting up the initial weights and their standard deviations.
Also, I don't quite understand how that works technically, but yeah, it sounds like an interesting thing to try, but I don't really understand how it works technically, so I think it would be like a nice thing to try to implement.
Yeah.
So
it's somewhat foggy for me.
One question, before this, I think they pronounce it initialization.
Yeah.
Wasn't it the Xavier initialization which used to have this mean of 0 and standard deviation of 1? I'm just asking.
Sure. So Xavier, did you say?
Yeah, Xavier initialization.
Yes.
No, it's not the mean of 0 and standard deviation of 1. It's just a different scaling factor. So this Xavier initialization, it was invented for 10H activation function, which is linear around 0. And ReLU activation function, it's like shifting statistics in a different way. So this her initialization is was invented to work better with ReLU as compared to 10H. And the idea is to keep the mean around like 0 or constant, and standard deviation of activation around 1. So to avoid vanishing or exploding gradients, you know?
Yeah.
Yep.
So.
Yep, cool. And then they have a final thing which they do, which is the pixel normalization layer. And says added after each convolutional layer in the generator. It normalizes each activation based on all the activations in the same image and at the same location, but across all channels, dividing by the square root of the mean squared activation. So it's a elliptical code, and says this technique avoids explosions in the activations due to excessive competition between the generator and the discriminator. I can sort of understand the explosion, but I don't fully understand how it interacts with the generator and discriminator, I must confess. I can kind of understand what they're doing, but yeah, I don't know if either of you understand what that's about.
No,
this is also not quite like clear at technical level to me, but yeah,
I can sort of intuitively understand what they're trying to do, but I don't understand why this competition would drive it up, and you have to do this normalization to fix it. But yeah, interesting. Carrying on. So it says, and then we've got this issue with trying to decide the quality of the outputs. How do we measure that? And says one technique is to use human raters, but this is costly and time consuming. So the authors proposed to measure the similarity between the local image structure of the generated images and the training images, considering every scale. This idea led to another groundbreaking innovation, style GANs. So yeah, again, I don't fully understand what they mean by local image structure at every scale. I mean, I can understand every scale, but like, what feature is it that they're detecting to be able to say that the structure is the same between two different images scaled at a certain point? Yeah.
So what does the scale means? It means you add the different feature map and then say the feature maps kind of like are same. What do they mean by actually the scaling in this case?
Yeah, I just assumed that they meant just scaling the images, the outputs and the inputs, that at every scale size, that the structure was the same.
So what does the scale means in that sense? Scaling an image means like it's a feature map gets scaled?
No, just the size of the images. I mean, these are comparing images.
Oh, so in a sense, like go from 28 by 28 all the way to 1024 by 1024 and then do the comparison? Is that what it means?
I'm sort of assuming, yeah, that every scale, they're doing some kind of comparison between the images.
Yeah, I believe it's like you can look in fine grain scale, like to see that, say, hair or fur is looking realistic, and you can look and like higher scale to say that, okay, this looks like borders between objects are realistic. So this is some kind of quality measure, right? So yeah. It should probably like say if the picture is blurry or not, or if the edges are sharp or not, and stuff like that.
Yeah, yeah.
Okay.
Okay, so and then moving on to the style GANs. So the state of the art in high resolution image generation was advanced once again by the same NVIDIA team in a 2018 paper that introduced the popular style GAN architecture. The authors used style transfer techniques in the generator to ensure that the generated images have the same local structure as the training images at every scale, greatly improving the quality of the generated images. So, okay, we'll have a look at this structure in a second. The discriminator and the loss function were not modified, only the generator. So let's take a look at the style GAN. It is composed of two networks. So we've got a picture here. So we've got this network here and this network here. So this is what we're talking about. And then the first network, which is the mapping network, which is this guy here, says an 8-layer MLP, so it's like just a multi-layer perceptron that maps the latent representations, the codings, to a vector W. This vector is then sent through multiple affine transformations, i.e. dense layers with no activation functions represented by the A boxes, which produces multiple vectors. These vectors control the style of the generated image at different levels, from fine-grained texture to high-level features, or in short, the mapping network maps the codings to multiple style vectors. So let's have a little look. So where first of all, the latent representation, the codings come in here, there's some normalization happened. Then we've got this layer of MLPs. So there's no activation functions here. These are just simple linear layers. And the output of that is some kind of a vector, is a multidimensional vector. And then there are these individual A's at different layers that are passing into this synthesis network. So the idea, the output of this guy is going into each of these guys, and these guys are picking out kind of different features at different layers.
So question, so these A's are different weights, set of weights, like
so that says so dense layers with no activation. So dense layers with no activation function represented by the A box. Yeah, so they are dense layers. So each one of them has its own weights. Yes.
How each have different weights, because it's coming from all of them. So the latent vector Z goes through all these 8 layers, and then a final vector we're going to go at the end of this in the cloud W. How is going to be different weights in a sense?
So what we're saying is that each one of these is a layer, basically. It's like a dense layer. So it's taking as input W and producing some output, which is going into into this network. So that's why it's got weights, because it's just a dense layer.
Yeah, but
so
then
it would be nice if you called here so A1, A2, and so on. But
yeah, they shouldn't have called it all A. I mean, even all these are called B, and they should be probably B1, B2, B3, B4, because they're not necessarily all exactly the same. But you're quite right. I mean, even these, they're FC. They should be FC1, FC2, because these are all individual. They're individual weights. They're not all exactly identical. Yeah.
Yeah, but then that's the confusion. Why? So because the latent vector Z going through all these MLPs, and they coming out at the end of the network. So at the end of the network, you're gonna have just a one vector W.
Yes.
Which is A.
No, so that's still W there. You can imagine that's a 1,000 dimensional vector or something like that. Yeah.
Yeah.
And then that 1,000 dimensional is going to go into this dense layer, which could be any shape. So the output of this guy could be, say, 100, because it's only picking out certain features at that layer. Yeah.
Okay, so we are saying we pick up the first 100 and then push it to the A, and then next 100 to the next A, next 100 to the next A, and so on and so forth. Okay.
And because these are at different layers within this network, the idea is that these guys will pick out different features at different layers of the network. So one could be very fine-grained, another one could be sort of like high level, depending on what, because that's only a 4x4 image, whereas later on, obviously, it could be getting bigger and bigger.
Yeah. Okay.
So that's the mapping network, and then they've got the synthesis network. So this is responsible for generating the images. So the synthesis network is the one on the right-hand side. So this guy here. So responsible for generating the images, it has a constant learned input. To be clear, this input will be constant after training, but during training, it keeps getting tweaked by backpropagation. It processes this input through multiple convolutional and upsampling layers as earlier, but there are two twists. So let's have a look. It has a constant learned input. okay, so this is the constant. This is a learned input of some sort. So this is across the whole set of images. So this, okay, so that guy. But it is tweaked during, so to be clear, this input will be constant after training, but during training, okay, so during training, this guy will get updated to contain some additional information, but once it's fully trained, that is constant when you're using it in real life, okay. So it processes this input through multiple convolutional and upsampling layers as earlier, but there are two twists. Yeah, so there are multiple upsampling, and so there's an upsample there and convolution layers as well. Is everybody okay so far? Because I know I'm kind of slightly rushing through this.
No, it's fine. Yeah, it's a bit of a complicated piece of work.
Yeah, and then says, first some noise is added to the input and to all the outputs of the convolution layers. So we've got, so the noise is coming in, so it's going into the, as an input, into the original input, but it's also going as an input into the convolutional layers as well. So, and this B is the noise that's coming in. So yeah, so you're getting features from this side, some noise from this side, and then going into the network, and there's lots of noise at different layers being added. Yep. So that's the main architecture. Okay, so why are we doing all this? Second, each noise layer is followed by an adaptive instant normalization layer. It standardizes each feature map independently by subtracting the feature map's mean and dividing by a standard deviation. Okay. Then it uses the style vector to determine the scale and offset of each feature map. The style vector contains one scale and one bias term for each feature map. So the style is this A, it was the output of the A. So this is where the style transfer is happening. The idea of adding noise independently from the codings is very important. Some parts of an image are quite random, such as the exact position of each freckle or hair. In earlier GANs, this randomness had to either come from the codings, which is from these guys, the latent representations, or by some pseudo-random noise produced by the generator itself, giving it some way to generate some noise. If it came from the codings, it meant that the generator had to dedicate a significant portion of the codings' representational power to store noise. This is quite wasteful. Moreover, the noise had to be able to flow through the network and reach the final layers of the generator. This seems like an unnecessary constraint that probably slowed down training. Okay. And finally, some visual artifacts may appear because the same noise was used at different levels. If instead the generator tried to produce its own pseudo-random noise, this noise might not look very convincing, leading to more visual artifacts. Plus, part of the generator's weights would be dedicated to generating pseudo-random noise, which again seems wasteful. By adding extra noise inputs, all these issues are avoided. The GAN is able to use the provided noise to add the right amount of stochasticity to each of the images, to each image. Does that kind of make sense as why they've added the noise from over here directly as an input rather than trying to get the network to somehow generate it or put some noise inside the coding?
Yeah.
Okay, cool. And so the added noise is different for each level. So yeah, so each level of the network's got its own noise. Each noise input consists of a single feature map full of Gaussian noise, which is broadcast to all feature maps of the given level and scaled using learned per feature scaling factors. This is represented by the B boxes. Yeah, so the noise is fed through this B, which does the scaling before it is added.
What does it mean? The added noise is different for each level. So what does it mean? That means like it's a B1, B2, B3, different kind of a noise we are pushing in.
Yeah, so basically they're all independent. I mean, they're all from this Gaussian distribution, but so the data is not identical. So there'll be different data coming into each of these guys. Okay. And the reason is that you don't want the noise to be correlated, because this bit of noise might be generating some freckles and that bit of noise might be generating some hair, some differences in the hair. Yeah. And the two are not correlated. So that's why you have to have completely independent noises going in at the different layers.
Yeah.
Yep. And then there's some scaling to be done, because depending on the feature map, and that scaling is learned through this B. Yep. So finally, StyleGAN uses a technique called mixing regularization or style mixing, where a percentage of the generated images are produced using two different codings. Specifically, coding C1 and C2 are sent through the mapping network. So the C1 and C2 go through this network, giving two style vectors, W1 and W2. Then the synthesis network generates an image based on the styles. Sorry, guys. Then the synthesis network generates an image based on the styles W1 for the first levels. So that's the first levels uses W1, and styles W2 for the second levels. For the remaining levels, sorry. Okay, so the very first level uses W1, and then W2 is for all the rest of them. Yeah, so they've done something. So for each image, they generate two codings. Yeah, so they said for each image, they generate, so where a percentage of the generated images are produced using two different codings. Okay, so for some images, they have two codings, and then they use the two codings to generate two different weight vectors. And then one weight vector goes to the first layer, and the other weight vector goes to all the rest of the layers. Does that make sense of what they've done?
No. Can you repeat that again, please?
Okay, so this is for some percentage of the images, not every image, but for some images, yeah. What they do is they compute two different codings for them, C1 and C2.
Yeah.
And then they pass C1 through it to get like a weight to get this style vector. Yeah. And then pass C2 to it to get another style vector.
Yeah.
Yeah. And then the first weight they pass to the first layer. So these guys. The second weight they pass to all the other layers.
Okay. Yeah.
So that's what they physically do. But what's the consequence of this? Okay. So the cutoff level is picked randomly. Oh, okay, sorry. So it's not just the first. They choose a random cutoff. The top guys get W1 and the bottom guys get W2. Okay. So yeah, so this prevents the network from assuming that styles at adjacent levels are correlated, which in turn encourages locality in the GAN, meaning that each style vector only affects a limited number of traits in the generated image. Okay, so they're trying to stop the network from assuming that because the weights were sort of passed through to each layer, that all the weights are kind of in some way correlated, I guess. Is that kind of right, Arthur? Because that's sort of what I'm thinking, what they're doing.
Well, I like to understand this network, I want to first understand what is their original goal of using it. So what does it do? It just just from the name, I was like assuming that it might be used to transfer style between images, but it seems like it's not the case, right? So it just generates random images determined by this with some style, right?
Yeah, and so this bit of it is really to stop the network kind of assuming too much about the styles that are passed in, because the particular vector is going to pass through every layer. It's trying to convince it not to put too much so the adjacent pieces of the network don't assume too much about the weight vector, because this additional thing is going to randomly give some different weights to some part of the network to the other. It's going to stop it trying to correlate the weights between them. Yeah, so it's not as if it's going to say a particular position in this word vector represents something, because it's going to be past two different weight vectors, which I'm assuming are not going to have the same kind of value in a particular dimension. So the network's not going to try and say, oh, okay, dimension 10 is this, this, and this. By having two different weights, it's going to do something slightly more interesting.
So, and where is this latent style representation came from here?
Well, this style, it's learned because it's going through this.
Latent Z one, the original one, it's not random, right? It's some representation of a desired style.
Yeah, so again, so we're assuming this is part of the encoder network. So the coding is the output of the encoder network, or the generator network. So so just like a normal autoencoder which generates codings, this is, so we're missing some part of the network here, which is the bit that's generating the codings. Yeah, the latent representation.
So it's just not quite clear for me if this latent style representation is learned like together with all this generator network, or it could be like independent thing.
Yeah, that's a good question. I'm going to make an assumption to say it's all end-to-end. I would be very surprised if it's not end-to-end.
Yeah, I would also expect that, but it just without the whole picture, it's still somewhat foggy how all this thing works, and why do we need these two W's in the end? So because the two W's come from two distinct codings, and the question is how the codings are trained, and then we come if the codings are trained end-to-end together with generator, this means that we train two codings simultaneously, right?
Yeah. And if it's the same image, why would it? I mean, okay, there's some stochasticity in there, but I'm assuming that the codings are fairly similar. I mean, they shouldn't be fundamentally different if it's the same image. They'll be within the standard deviation of that kind of coding, wouldn't it?
Yeah, probably it would be like nice to read the whole paper to see the like wider perspective on this.
Yeah, are you volunteering? Because it's going to be a really hard paper, I reckon. I mean, it's going to be like, where is this one? Can I open it? Open it. I wonder how many pages it is. So style-based.
Well, the ideas for connected to GANs don't seem like really hard, but it's more like it's hard to make it work properly, right? Like all those like small tricks, they make sense, but the hard part is how do you came up with a good set of tricks to make this work?
Yeah, I'm assuming there's some big images in here. That's why it's taking so long to download. Oh, it's only 12 pages. Oh wow, yeah. There's just lots of images. That's why it's quite a big yeah, I don't know. I mean, I don't mind us all reading it together, or I don't know if you fancy reading it and maybe doing one of the paper readings on it. I know it's not NLP, but it's only a couple of us, and we don't mind reading different papers.
Yeah, sure. But, I had like have a look on a couple of other papers, and there is like a lot of different stuff related to GANs. And I just wasn't sure what is the best one to take a look at. I was just watching that lecture from Jeremy Howard, his course, and he had a couple of different papers. Also, there was Wasserstein GAN, which is like kind of similar to the one we considered in the previous section, I guess. And there was cycle GAN, which is used for style transfer. So what it does, it takes like in their example, there was some images of or even video of horses, and it was transferred to videos of zebras. It's called
Oops, what does that look like? Yeah, they're all giving this aspect of it, but like, where's the latent bit coming from? Yeah, there must be a picture of it with the latent bit as well. Yeah, unfortunately, they're all going off the picture in the paper, which only sort of just says input is a latent.
Yeah, yeah, probably worth taking a look at it, because what I'm interested is how do you control this latent representation, which you further use in your model to like control the generation, because it's also relevant to NLP and generating diverse but controlled texts. I guess some experience from here can be transferred to NLP applications.
Oh, yeah, so there's a PyTorch implementation. I mean, I haven't got the time to go into it at the moment, but we could, I guess, have a look at this guide to see exactly how they implement it.
Yeah, just what I think it's so to go into this stuff really is only worth it if you're going to train some of this, because otherwise it would be just like you wouldn't have this deeper understanding. I just played a bit with the simple GANs from the previous part of this chapter, and the results are, I would say, controversial. So most of the time, my this simple GANs degenerate to producing very similar images every time.
All right. Mode collapse, I guess.
Yeah, and maybe I will slowly build up on that, and when I have time, I will maybe experiment with that a bit more, like add some parts from this next sections and try to fix that mode collapse and see how it works, and maybe implement something from other papers. In that Wasserstein, again, they achieved some good effect by restricting gradients. So they were what were they doing effectively? They was just clipping the gradients in when training a discriminator with some really smaller range, and I believe that was causing some positive effect. And I didn't go into details on that, but there are lots of approaches you can take to this stuff, and it looks like there is no single one which works best. It's just you have to experiment with it.
Yeah. I mean, it's. I must confess, I'm interested in NLP. So if there's any papers related to GANs and NLP, I'm more than happy to fully read those and do them. But purely for image-related stuff, it's not really sort of my thing. But yeah.
There's some papers Matt didn't read those, but which were generating images from text, and we can maybe pick one of those and to have a look how you relate text to image, and there are quite a lot of that kind of applications.
Okay. Oh, that might be quite interesting. I'm interested in anything that's kind of generation related. So yeah, cool.
I'll pick some of those.
Okay, cool. Although they do explicitly mention they do not get discouraged if it has trouble learning at first. Unfortunately, this is normal and it requires quite a bit of patience before it works, but the result is worth it. Yeah, they're really temperamental. So as you say, you might, the people have obviously had to play with clipping gradients and doing all sorts of stuff to stop it from, going a bit crazy. Right. So I think that's it for this chapter. So yeah, I might have to listen to the guys on Sunday because unfortunately I missed that bit. While we're on tomorrow, I'm not sure I'm ready to do the full jacks and flags. So basically, I read up the documentation, so I understand jacks/flags. And actually, that's not too. Sorry, so this is for Arto. I don't know, Dinesh, you went there last week, but we were gonna for the NLP papers, we were gonna have a look at this framework from Google, which is called jacks/flags. So basically, I mean, if I explain to you what the situation is, so basically JAX is essentially a kind of subset of NumPy, but written for processing on GPUs and TPUs. And then Flax is kind of like a library built on top of JAX, which gives you all the primitives you need to actually create neural networks and train them. And Flax is very similar to actually PyTorch. If you look at the code, it's it's been kind of virtually lifted from PyTorch, because essentially you create a class which is subclasses from NN module, and you create the different layers, and you've got like a function which you apply the inputs and get the outputs from, and virtually the same sort of approach to optimizers and loss functions and parameters. The bit that I'm missing is that one of the nice features of Flax and JAX is that they've got some additional support for actually parallelizing across different nodes. So I wouldn't mind seeing if I can find some reference to that, because the examples I have didn't do that. And that's actually the main thing that I'm kind of interested in. So I don't know if you guys will be okay if we miss tomorrow, and hopefully by next week I will have gotten to that bit of it as well. Is that going to be okay?
Yeah, and I'm going to be random. Actually, I have a meeting set up alternate weekend, so alternate week. So tomorrow I'll be busy, and then next week I'll be able to. So perhaps I don't mind missing tomorrow. But
okay,
do you mind just throwing the paper in the channel itself, or any Medium post, or anything you want?
So I went over the so the JAX Flax documentation. So I was using, and they've got sort of example code on GitHub. Yeah. So this guy, I'll put it in the chat. And so it's relatively easy to read. As I say, if you know any PyTorch, you will recognize it immediately that this is very similar to it. So instead of using Tensor, PyTorch Tensor, you've got a kind of like I think, what's it called? Essentially sort of an array class in JAX. And it's got very similar operations to NumPy. So it's very similar to PyTorch. As the main thing I was interested in was this parallelism support that JAX and Flax. So they've got some architecture for doing that. But this documentation is really about the core library, which is how to build models, and how to train them. But they're all kind of like just standard models with multiple layers. So there's no parallelism or breaking up of any data or anything like here. It's all virtually like PyTorch, really. You send a batch of data into it, and but yeah, I'll paste this in the chat, which will give you documentation. There's a GitHub page with the examples of models, and they all look very similar to PyTorch. But it's the other bit which I was interested in, which was like, how would you use it in prod when you've got like a really large model and you need to train it in parallel, because they had that support for that. So let's have a little look.
The idea behind this JAX is to introduce better support to like parallel stuff and like TPUs, right?
Yeah. So the bit that I'm pasting here is really the core library. So where the hell is the chat gone? For some weird reason, I don't have it on here. So let me stop sharing to see if I can get the app. Oh, here it is. So I've just pasted in the chat that link to this documentation for it. And it's quite nice. It's got sort of some examples, links to some simple code. It's got some GANs as well, actually.
Yeah, that was DC GANs that we are going over today, actually.
Yeah. And as I say, most of these, as I say, if you've ever done any PyTorch, it's going to look really, really simple. But yeah, as I say, if you give me until next week, and I'll try and see if I can find out more about the parallelism, because that's the bit that I'm really interested in. Because as I say, so far, I don't see any difference between PyTorch and this thing. So other than the fact that obviously it supports TPUs, but even PyTorch supports TPUs now. There's a project to support TPUs in PyTorch. So I think we'll meet next week.
Right.
Sorry.
Good. Yeah.
Okay. So have a nice evening, guys, and I'll probably speak to you next week.
All right, fantastic. Thanks very much. Thanks.
Thanks then. Right. Bye.